This is Ravi Chandra. Today I am here to discuss about a new topic which is nothing but a realization of digital filters. In that a particular filter we are going to discuss, which is very important. That filter is nothing but FIR, which is finite impulse response. So in digital signal processing, these two filters are very important, and these we need to concentrate on this very much. Okay, so what are the contents I'm going to discuss in this lecture is, before directly going into the finite impulse response, just we will recall the thing, what is meant by a filter, what are the types of filters, and what is meant by a digital filters, and what are its classifications. And finally, after that, why we are going with this realization, what is the important thing to take this realization into consideration. So after that realization, how this realization FIR filter can be realized, and what are the types of method to realize this finite impulse response. So here some of the contents which I'm going to discuss in this particular lecture, starting with what is filter and what are the classification of filters, then followed by the digital filter and its classification, and how these digital filters are designed, and what is meant by realization. So with the help of this realization, how this finite impulse response is going to be realized, and what are the classifications of this finite impulse response and properties. So here, to design this finite impulse response, there are some different types of methods. In that, in this particular lecture we are going to discuss about two things. One is direct form, or also we can call it as transversal form, and one or two problems related to this, and followed by the cascade form, which is the problems which is related to the cascade form. So these are some of the contents which is going to discuss in this present lecture. So here, so what is meant by a filter? We know that in each and every communication systems, filtering is very important. Why? Because to get a good output or efficient output, what happens here, the signal which is obtained at the output side should be error free. So for that, this filtering is very important. Let us see what is the definition of this filter. So filtering is the process of selectively passing or attenuating specific frequency components. So these are the components we need to attenuate. Definition, what is meant by filtering? See here, filtering is the process of selectively passing or attenuating the specific frequency components. So here the attenuation of some specific frequency components of a signal to extract the desired information or reduced noise. So for example, just observe this particular graph. This is the signal which is affected with some noise, the original signal in a time domain which is affected with a noise, and you can see the spikes, how this signal is obtained, and you can see the spikes, which is nothing but this signal is affected with noise. So to remove this particular noise, that means we need to select that particular frequency components, and we need to attenuate that things. So after selecting that particular frequency components and attenuating that particular components, what happens here, the exact frequency signals will be, or the exact desired information will be obtained. You can see the difference of this signal before filtering, after filtering. Okay, so before filtering you can see some noise is affected to this particular signal, and after filtering, that means after selectively taking the frequency components and attenuating that particular frequency components, then this signal will extract the original signal, which is nothing but this one. So you can see the difference between both signals, that is signal affected with noise, and after filtering, what is the output signal we obtained at the particular system. So this is nothing but, filtering is nothing but is the process of selectively passing or attending some specific component to extract the desired input signal, desired output signal, or desired information at the output side. So this is nothing but filtering. So based on this filtering, these filters are being classified into, you can see some different types of classifications. First of all, in filtering, in signal processing, the filters are classified into, see here, low pass filter, very important, high pass filter, band pass filter, band stop filter, and all pass filters. These are the main important filters which are present in the signal processing, the different types of filters which is present in the signal processing. So here, coming to the another classification, depending upon the implementation, these filters are being classified into two types. One is analog filter and second one is digital filter. You can see this word classification based on the implementation. That means because of this implementation, this classification has been done into two types. One is analog filter and another one is digital filter. How this implementation for analog filter? Implemented using resistors, capacitors and inductors, op-amps, some different types of devices. These analog filters are being implemented. If that particular filter is implemented with some different types of active and passive components like resistors, capacitors, inductors and op-amps, that types of filters is said to be analog filters. Now second one, digital filters. So some different types of filters which is implemented with the help of digital logics. This is digital logic and analog and algorithms. So for example, this FIR and IIR filters. So depending upon that means implementing that particular filters with the help of digital logics and algorithms, then that types of filters is said to be a digital filters. So second classification is that based on the implementation. Two types, one is analog and second one is digital filters. Now third one, now here this is very important. Based on the impulse response of that particular system, these filters are being classified into two types. One is FIR filter and second one is IIR filters. Very important in this, which is finite impulse response filters and infinite impulse response filter. So depending upon the word, this is the word, you need to keep it in mind. Depending upon the impulse response of the system, the filters are being classified into two types. One is FIR filter and second one is IIR filter. So FIR filter, when we call it as a FIR filter, output depends on current and past input values. Please keep it in mind. When the output depends upon current and past inputs, then that type of filters is said to be a FIR filters. Now infinite impulse response, when we call it as IIR, when the output depends both current and past input values and output values. See here, when the output y of n depends on both current value, that is x of n, and past value x of n minus 1 and output values x of n plus 1. So if it depends upon all the things, three things, then that type of filters is said to be a IIR filters. So based on the definition of the filters, the classification has been done like this, depending upon the signal processing: low pass, high pass, band stop and all pass filter. Depending upon the implementation, the filters has been classified into two types: analog filter and digital filter. And depending upon the impulse response, this has been divided into two types. One is FIR filter and IIR filter. Okay. Now here comes, what is a digital filter? We are entering into the digital. Why? Because we are discussing about the digital signal processing. Analog, we know that whatever the signal we are giving analog, it should be converted into digital, and then only the filtering will be taken place. So here, that's why we call the term it as a digital filter. So when we call it as a digital filter, same. A digital filter processes a signal by taking its digital form, that means pulse form. By taking its digital form, a series of numbers, that is zeros and ones, whatever it may be, a series of numbers, and adjusting it to remove noise, and adjusting it to remove the noise, and hence enhancing the specific parts or focusing a certain frequencies, resulting in a clear or more useful output. Similar definition only. It is similar to that of filtering, but what happens here? We are considering the digital signal. That's why a signal, by taking the digital form, that is the number of the sequence, the series of numbers, what we are going to do here? We are adjusting the noise. That means we are going to remove the noise. After removing the noise, we are enhancing that particular signal. And where we are enhancing, that means by focusing on some particular frequency components, we are going to enhancing that particular specific parts, and resulting what happens here? We are going to get the clear and more useful output. So this is the term what we are calling it as a digital filter. See, small block representation. So we are taking the analog form. You can see here we are taking the analog form. So with the help of analog to digital converter, this is converted into the discretized form, and here comes the processing core. So in this scenario, in this conversion scenario, what happens here? The noise is affected. So what happens? The noise is affected. So here, after converting into the digital, based on some digital filters, what we have discussed in the previous slide, with the help of some particular filtering process, these digital process are going to filtered, and some noise will be removed and some specific parts, it concentrates on some specific parts like frequency components, and here some noise will be removed, and finally what we are going to get? We are going to get the digitalized signal with filtered. So this green signal is said to be a digitalized filtered signal. After filtering we are going to get the exact digitalized filtering signal. So here the orange signal is nothing but sampled digitalized signal. Sampling means both sampling and quantization has been done here. While doing that process, this signal will be affected with some noise. So with the help of this processing core, with the help of this digital filtering process, this signal will be filtered, and after filtering this green signal, you can see the green signal representation, which digitally filtered signal, which is digitally filtered signal, where that affected noise will be removed, and finally it is given to the DAC. That means digital signal is converted into the original signal. See here, whatever we are giving here as analog signal, the same should be formed here. The analog signal should be formed exactly without any noise. Without any noise, the signal should not form. See here, we can see here, without any peaks, whatever we have given here, the same thing is formed at the output side. That means this process is said to be a digitalized filter. Where we are filtering that signal, we are filtering the signal for the digitalized, the number of series, the series of numbers. See, the series of numbers we are filtered. So that's why we are calling it as a digital filtering process. Okay. Now, based on this digital filter, we will see some characteristics. So what are the characteristics that involves in this particular digital filter? First, digital filters are characterized by the impulse response. Very important. Based on this particular impulse response, the digital filters are characterized. The first one is, a filter's impulse response is its output when the input is in impulse. Okay. Impulse response is its output, y of n, when the input is an impulse. Okay, when the input is an impulse, automatically the output should be also an impulse response. Second one, impulse response determines the system behavior. This is the main thing, how the system is behaving. So with the help of this impulse response only, we can determine whether the system is behaving perfectly or not. So this is the heart. The impulse response is the heart of that particular system behavior. Whether the system is correctly producing the correct output or not, this will tell by the impulse response of that particular system. And completely, whatever the system we are using, it will be in a linear time invariant system. Okay, the system what we are using, it should be completely linear time invariant system. And finally, based on all these three characteristics, uniquely determines the frequency response. So based on depending upon this particular all characteristics, these digital filters, depending upon the impulse response, has been classified into two types. One is FIR filter and IIR filter. Previous slide we have seen the classification of digital signal based on the impulse response. The classification of the digital signals, digital filters based on the impulse response has been classified into two types. One is FIR filter and another one is IIR filter. So FIR is nothing but finite impulse response and IIR is nothing but infinite impulse response. So in this lecture, we are going to discuss about what is meant by FIR filter. Okay. Now here, how these digital filters are going to design? What are the steps that involves in designing a digital filter? So that may be a FIR filter or IIR filter. How these digital filters are going to design? Let's see what are the steps involved in designing this particular digital filters, whether it may be a FIR filter or IIR filter. So what are you saying? Digital filter design is the process of creating a digital hardware or software, whatever it may be. If you want to design the digital filter, we can use both hardware and software solution that meets the specific filtering requirements. Okay, so we can design this digital filter both in hardware process as well as software process, where we should meet the required specific filtering requirements. So now we discuss mostly on the digital hardware, how these are going to design. So the key steps, first one, define the specification of the filter. Whatever the parameters that involves in that particular system, first we need to define that. So define specifications. Please keep this word in the mind. defining the specifications. What the filter have the specification? First we need to define that. We'll see that in the upcoming problems. What are the specifications? Now, select the technique for coefficient evaluation. So what the technique is very useful. That technique is going to selected. So we have some different types of techniques which will come across the upcoming lectures. So we need to select the particular techniques or particular methods how to evaluate the coefficient. The coefficient is nothing but BK. Fine. Now after selecting the techniques, now based on the particular techniques and based on particular system, we can choose any filter. That may be a FIR filter or IIR filter required, which filter is suitable for that particular system. Okay. After selecting the technique, we are evaluating the coefficient. So after evaluating the coefficient, we can choose either which type of filter is suitable for that particular system. That may be a FIR filter or IIR filter. And finally, after analyzing that, after choosing that particular filter, we are going to analyze the finite word length effect, and finally whatever the finite word length here appeared, that is maybe h of z, it will be realized or implemented with the help of digital filter. So these are the main 5 important steps how we are going to design the digital filters, whether it may be a FIR filter or IIR filter. So first what we are going to do, we are taking the specifications of that particular filter. Secondly, we are evaluating the coefficients by using some different types of techniques. Third, we are going to choose either FIR filter and IIR filter based on the requirement. And fourth, we are analyzing the finite word length. After analyzing length, that particular analyzed finite word length will be implemented with the help of the digital filter. So these are the main key factors that involves in the designing of the digital filter. Fine. Now, so what is the realization? What is the main importance of this realization and why we are using this realization means? You can see it is a process of converting the transfer function in a block diagram. So after doing all the steps which we have seen in the previous slide, after getting this transfer function, these will be converted into the block diagrams. These will be converted into the block diagrams, block representations. We will see that. We will see that in the next upcoming slide. So after getting this h of z equation, this will be converted into block diagram representation or software program. So realization is nothing but it is a process of converting the equation, the transformed equation, that will be converted into the block diagram representation. So this block diagram or software representation is referred as realization. That means converting the equation into block diagrams. That process is said to be a realization. Fine. Now, why this realization? What is the need for converting this equation into the block diagram means? Ensure the design is a practical, simple and cost effective. Okay. So after conversion, that block representation ensures that design practical, simple and cost effective. Optimize the filter for minimum word length and high dynamic range. That means that equations can be minimally word length and it will be high dynamic range. And finally, it calculates the numerical value of coefficients from the transfer function. So when it is in a transfer function h of z, it is somewhat difficult to calculate the coefficients. When it is converted into the block diagram, it will be easy to calculate the different types of coefficients that is present in the transfer function. So these are 3 important things which shows that why we are going with the realization. So based on this realization, how this FIR filter, finite impulse response, are going to realize. Before that, what is meant by FIR filters? So it says that a finite impulse response filter is a type of digital filter where the impulse response settles to 0. The impulse response settles to 0 in a finite duration, countable in a finite duration. Okay, whatever the impulse response, it will be settled to 0 in a finite duration. That means it should be countable. And what are the characteristics? The characteristics of this finite impulse response, it is linear phase response, always stable. There will be no feedback in this particular FIR filter, and it will be always stable and very easy to implement all the convolutions. Very easy to implement all the using the convolutions. And finally, more taps required than IIR filter. Taps is nothing but some delays. We'll see that in the next upcoming slides. And what is the formula? It says that y of n is equal to FIR filter. y of n is equal to summation h of k, which is impulse response, into x of n minus k, which is input. It is an impulse response, it is a input. So I told you impulse response settles to 0 and it should be a countable. That means it should be a finite duration. So by combining all this, y of n is equal to summation h of k into x of n minus k, which is the formula for the finite impulse response. What is h of k? H of k is the filter coefficient or impulse response. So based on this particular equation, what are the properties of these FIR filters? So as we already seen that FIR filters uses set of coefficients, a set of coefficient to define their behavior and determine the filter output. The set of coefficients, see here, the set of coefficients which it defines the behavior of the system and determines the filter's output. So this is the mathematical representation of the FIR filter, that is y of n is equal to summation k is equal to 0 to n, k is equal to 0 to n minus 1 bk x of n minus k. So what represents here? Here x of n minus k is nothing but the input signal, bk is nothing but the coefficient that shapes the filter. This plays a major role. bk is nothing but the coefficients that shape the filter. Why it is shape the filter? Why? Because set of coefficient to define their behavior and determine the filter output. So it is the major factor that shapes the filter's response. And what is y of n? Which is nothing but the output of that particular filter. And here capital N represents the filter order, that is number of coefficient, whether it may be a n is equal to 1, 2, 3 and so on, 4 and so on. So it represents the filter order. So based on this, each coefficient influences the amplitude and phase of the signal, enabling specific filtering operations such as smoothing, sharpening, attenuating certain frequencies. As I told here, which is the bk is nothing but the coefficient which shapes the filter's response. How it is going to shape the filter's response? Because of this coefficient which influences the amplitude and phase. It influences the amplitude and space. So by and enabling the specific filtering operations. What are the specific filtering operations? It smoothens the signal, it sharpens the signal, or it attenuating the signals. So by doing all these things, the particular shape of the filter response will be obtained. Okay, so that's why that's why bk is said to be a coefficient that shapes the filter response. How? Because of these particular operations. Fine. Now classifications. So I told you, based on these equations, FIR filters are characterized depending upon the characteristics These FIR filters has been classified into four types. One is direct form structure. That means how these FIR filters can be realized. What are the techniques that involves in realizing these FIR filters? First one is direct form structure, cascade form structure, linear phase structure and frequency sampling structure. These are some of the important structures or techniques which is used to classify the FIR filters or which is used to realize the FIR filter. Fine. Now we will see in this lecture, we will discuss about the direct form structure and cascade form structure with one simple example how these particular FIR filters are going to realize with the help of these two structures. So we'll start with the direct form structure. What it says, the system function of an FIR filter, we know the equation of the FIR filter, that is h of z is equal to summation n is equal to 0 to n minus 1 h of n z power minus n. So this is the transfer function of the FIR filter. So after expanding this summation, if I expand this summation from n is equal to 0 to n minus 1, how? H of 0, that is h of n is equal to and z power minus n plus h of n z power minus n. That means first n is equal to 0, we are going to get this one, and for n is equal to 1 we are going to get, for n is equal to 2 h of 2 z power minus 2 and so on. For n is equal to n minus 1 h of n minus 1 z power minus of n minus 1. So I expanded the summation. After expanding the summation, this is the equation I got. Now what is the impulse response here? we know that h of z is nothing but the impulse response. So I can write this h of z as output by input. What is y of z? Y of z is the output and x of z is the input. So h of z is equal to ratio of the output by input, that is y of z by x of z, and the summation expansion equation. So what I am doing now, I am cross multiplying this. I am taking this x of z to right hand side and multiplied. So I got what y of z is equal to h of 0 into x of z, z power minus 0, plus h of 1, z power minus 1 into x of z, plus h of 2, z power minus 2 into x of z, and so on. That means I multiplied this x of z to all the factors on the right hand side. So based on this particular second equation, so I am going to realize the structure. So after realizing, so you can see here what we have done. We have done the transfer function. We have converted the thing into transfer function. So now what we are doing, we are realizing, and we know that what is meant by realization? Converting the transfer function y of z into block diagram. So after getting the transfer function, what I am doing, I am converting the transfer function into the block diagram representation. That's why we are calling it as a realization. Okay, now we will see how this particular diagram is to be realized. Now first, this is the basic structure. Depending upon the second equation, this is the basic structure, and we'll see simply we'll see how can we draw this one. So in this cascade direct form, first draw all the delays. How many delays is there? You please draw. So we can see the delays is z power minus 1, z power minus 2, and so on, z power minus of n minus 1. So z power minus 1 is 1 delay, z power minus 2, z power minus 3, and so on, z power minus of n minus 1. First what I have done, I have drawn all the delays. Okay. So of drawing all the delays, now next to see what are the impulse responses, that is product of that particular x of z. So I have drawn next h of 0, h of 1, h of 2, next so on, h of n minus 2 and h of n minus 1. And please be careful while representing these arrow marks. These arrow marks will play a major role. If these arrow marks are kept in wrong direction, the equations what you have drawn, the equations will get in wrong, equations will be formed. So what second term I have done here, I have drawn the all impulse responses between the delays. So here one response and second response between two delays, third response, fourth response, fifth, and so on. All delays have drawn here. Now, third step, please draw all the adders. Connect all the adders to the impulse responses. See here, connect all the adders to the impulse response. Whatever the impulse response line I have drawn, I have connected all the adders. Fine. Now, here forms the major block diagram of the direct form of the direct form of the FIR filter. So what is the main thing here? X of z is a common factor for all the thing. Now if you see here, just take one. What the term I am going to get here? X of z into h naught, x of z into h of 0. Okay, I got here for place. That's the first thing. H naught into x of z. Now see here, x of z into z power minus 1. What I am going to get here? X of z into z power minus 1, and what is the product here? Multiplied h of 1. Okay, so what I am going to get? X of z, see here, x of z, next z inverse, next h of 1. So I got the second term. Here what happens? These two are plus. Now here another term. What is the another term I am going to get here? Same, x of z, z power minus 2, h of 2. So this is the second term I got here. So plus first term, second term, third term. So after getting here total what I am going to get? I am going to get the three terms like this. After doing all the things, I am going to get this total term, that is y of z is equal to all the adding of all the terms which is formed here will get the transfer function of the FIR filter. I think it is, you get a clarity about this particular diagram, how we need to draw the diagram if it is in a direct form. Okay, so what it says, these structures is known as transversal structure or direct form realization. the direct form structure shown above looks like a tab delay. You can consider all this as a tabbed delay lines. All the it will be in a tabbed delay lines or transversal system. Hence, direct form realization is also called as transversal or tabbed delay line. So, we can call with any name. We can call it as a direct form or transversal form or tabbed delay line. You can see the delays all will be in the form of tabbed form. Okay. And how many adders and how many delay elements? So, this is the thing we need to keep it in mind. So, in the transversal structure, in the direct form structure, how many adders are and how many delay elements are required means, here total number of multipliers is n. How many multipliers we are going to require here? See here, multiply 1, 2, 3, so on. N multipliers are required. And how many adders is required? 1, 2, 3, so on. Whatever the adders here, that many adders required. So, how many adders is required in this particular direct form? N minus 1 adders. Okay, N minus 1 adders. And similarly, how many delays? Same, N minus 1 delays. So, with this, whatever the problem we are going to get, with the help of that particular problem, by using this simple structure requirements, how many multiplication has been done and how many additions and how many delays are obtained with that particular in that particular problem, we can identify with the help of these requirements. Okay, so this is the direct form realization, how this FIR filter can be realized with the help of a direct form. So, can we take one example now? So, consider one example. Determine the direct form realization of the system function h of z is equal to, here they will give h of z, which is the transfer function, system function, that is 1 plus 2z inverse minus 3z power minus 2 minus 4z power minus 3 plus 5z power minus 4. Please keep it in mind, first of all, you have to be in a good thing to keep it in mind, that you should be in a good practice. You should be very careful that if whenever for the upcoming problems, whatever the problems which is coming next of this direct form, whenever you are confident with this direct form structure, then you can able to draw the things which is coming in the next lectures. Okay, that's why you should be very careful and very need to very confident in doing this direct form. When we are very confident in doing this particular direct form structures, automatically you can do all the realizations which is coming in the next slides. Okay, now that's why I am asking you to be very clear to make it clear that you should be very confident in doing these particular structures. Okay, so determine the direct form realization of the system functions h of z. So, how? First, what we are going, h of z is equal to, they have given, though I am writing this h of z in the form of y of z into x of z. Okay, and what I am doing, I am multiplying all this x of z into the right hand side, so that the finalized equation y of z is formed. Previously what we have seen, same I have done here. So, how many delays here? 1 delay, 2, 3 and 4 delays here. Okay, keep it in mind, how many delays? 4 delays. So, after doing this small simplification, the finalized equation what I got here is y of z is equal to 1 into x of z, 1 into x of z, 2 into z inverse x of z, minus 3 into z power minus 2 x of z, minus 4 into z power minus 3 x of z, plus 5 into z power minus 4 x of z. So, now what happens? We have taken this, converted this h of z into y of z, the transfer function output y of z. Now, what we need to do? We need to realize this particular transfer function. That means we need to convert this transfer function obtained into the block representation, block diagram represented. That means we are realizing the above equation. So, how it comes? I told you, how many delays are there? You need to draw that first delay. So, first delay z power minus 1, z power minus 2, z power minus 3, z power minus 4. Okay, 4 delays I have drawn. Next, I told you to draw the multiplied product terms. What is here? 1. So, here 1, next second term, next minus 3, next minus 4 and next plus 5. I told you, draw the products which is multiplied, draw the terms which is the product of the delays. So, that is for z power minus 1, the delay is the product, the term is which is multiplied is 2. For Z power minus 2, the term which is multiplied is 3. And for Z power minus 3, the term which is multiplied is minus 4. And for Z power minus 4, the term which is multiplied is 5. So I have drawn. Then connect all these particular things for the adders. First adder, second, third, fourth. So all I connected. Okay na? All I connected. Please be careful while drawing this and while mentioning the arrow marks. Okay. Now if you see here, first term x of n, this is a common term. Why? Because for all the equation which is you can see here, for all the terms x of z is a common factor. That's why input x of n is a common factor. So what is the first term here? 1 into x of z. This is the first term. What is the second term? X of n, that is x of z. Second term what I am going to get? X of z into what is the coefficient here? 2 into z power minus 1. This is the second product, plus the what is the third term here? X of z power minus 2 into minus 3. Okay, this is the third term. And what is the fourth term here? Same x of z, which is a common. And what is the delay term here? Z power minus 3. And what is the coefficient here? Minus 4. So this is the term. And what is the final term here? Same x of z, which is a common factor. And what is the delay term here? Z power minus 4. And what is the coefficient here? 5. This is the fourth factor. So 1 into x of z plus x of z into 2 into z power minus 1 plus x of z into z power minus 2 minus we are going to it. So whatever all the terms will be added finally, and finally what we are going to get? We are going to get y of z or y of n is equal to, this is the term. Very simple, very easy to realize this particular transfer function into the block diagram representation. So this is the direct form, how we are going to realize. And finally, another example you can see here. H of z is the transfer function given here. Applying the inverse z transforms after converting that y of z into y of n, rearranging the equation. So y of n is equal to x of n plus x of n minus 4 plus 3 by 4 into x of n minus 1. All I have rearranged the above thing. And finally what the equation I got here, you can see here input signal x of n, delay terms, how many delay terms we got here? 1, 2, 3, 4. 4 delay times. You can see here 4 delay times. Z power minus 1, Z power minus 2, Z power minus 3, Z power minus 4. Coefficients, how many coefficients we got here? 1, 3 by 4. Next 17 by 8. So 1, 3 by 4, 17 by 8, 3 by 4 and 1. So how many coefficients? 1, 3 by 4, 17 by 8 and 1. So totally we got all the things. And how we are going to realize? This is a finalized equation. With the help of this transferred equation, this is another structure, another style. We can draw this structure at any style. Previously that style is another, and this is also another style. So if you are familiar with anything, you can draw. But the equation should be, you should get the equation which is in a correct format at the output side. So this is another example for the direct form. So finally, we will discuss what is a cascade form. And it simply says that the name itself telling cascade. The cascade form realization is obtained by connecting second order sections in cascade form. See here, H of Z is a cascade form connection. How the impulse response H of Z into H2 of Z into H3 of Z and so on, Hk of Z, that are connected in parallel. So realize each section. That means here we have to realize the each section. First H1 of Z we need to realize, H2 of Z we need to realize, H3 of Z we need to realize, so on. And finally what we need to cascade. We need to connect the two things. Okay. What happens here? We will get the H of Z, which is nothing but the correction of individual impulse responses. So after that we need to draw the H1 of Z realization and H2 of Z realization. After drawing these two things, we are connecting that both so that it will be in the form of a cascade form realization. You will see that. Just take one example. H of Z is equal to, first H1 of Z, here H1 of Z and H2 of Z. The product of two terms, which is h1 of z, that is 1 plus 2 into z power minus 1 minus z power minus 2, and the second term is 1 plus z power minus 1 minus z power minus 2. You can see here h of z is equal to h1 of z into h2 of z. Now what the second thing we need to find? We need to do the separately we need to find out the direct form 1 for the h1 of z and direct form 2 for the h2 of z. First we will see what is the direct form for h1 of z. Consider h1 of z is equal to 1 plus 2 z inverse minus z power minus 2, and h2 of z is equal to 1 plus z power minus 1 minus z power minus 2. So first I am considering the h1 of z, where I am writing it as y1 of z by x1 of z. So I am considering first these term. Okay. So I am writing, instead of h1 of z, it will be y1 of z by x1 of z. So multiplying this term, I got the finalized transformed equation y1 of z. So one equation I got. Let it be a first equation. Now second, I am considering the second term, which is h2 of z, which is, I can write it as y2 of z by x2 of z. So taking that x2 of z into the right hand side and multiplying that, the second equation what I got here is y2 of z is equal to x2 of z plus z inverse x2 of z minus z power minus 2 x2 of z. So how many equations we got here? We got two equations, that is y1 of z and y2 of z. So two factors, two realizations we got. When we connect these two equations, then that particular diagram is said to be a cascaded realization. So we will see that in the below diagram. See here. So first what happens here, x of z is a common. Now this is the h1 of z direct form. Okay. First this conversion is the h1 of z, this diagram, and this diagram is a h2 of z. So after drawing these two diagrams, what we done here, you can see we have connected the two things where it has been connected parallelly. Fine. So that's why first how we have drawn this h1 of z. See here, x of n. What is the equation? X of n into z power minus 1 plus x of n into z power minus 2. So once you can see the x1 of z into 2 into z power minus 1, x1 of z minus z power minus 2, x1 of z. So first term what I am going to get here, x of z. Second term I am going to get x of z, z power minus 1 into 2, and what I am going to get, minus x of z, z power minus 1. Here plus, here plus. So h1 of z is equal to, I am going to get x of z plus 2 into z in power minus 1 x of z minus x of z into z power minus 2. So this is the total term I am going to get here. Now similarly, second equation also. See here, this is the first term I am going to get. What is the first term? x2 of z, and here I am going to get z inverse x2 of z, and here I am going to get minus x2 of z, z inverse. Total three things I got. So plus what I got here, h2 of z is equal to x2 of z plus z inverse x2 of z minus z power minus 2 x2 of z. So these two I am connecting here. So h1 of z I am connecting here and h2 of z I am connecting here, so that I am going to get y of z. So y of z is equal to combination of two diagrams, that is h1 of z first, that is y1 of z first diagram, and y2 of z first diagram, where finally I am going to get y of z is equal to y1 of z into y2 of z. So this is the cascade form. This is the cascade form how we need to draw. Fine. So this is based on the direct form. If we know the thing how we can draw the direct form, then only you can able to draw this particular cascade forms. So this is one of the example. Now here one more model, just we'll see, this is the final problem. This is the another model. What happens if the given equation is not in a product terms? For example, h of z is equal to, it is in the form of transfer function, where it is not in h of z is equal to h1 of z into h2 of z. It should be like that. Actually cascade means connection of two impulse response, but the equation is somewhat different. You can see here. So for that what we need to do, we have to do the partial fractions for these particular rationalized factors. After converting this equation into factors, so we are going to get h1 of z into H2 of Z. I think you got the point. We need to convert this particular into a factors, and it will be in the form of a product, that is H1 of Z into H2 of Z. Then again same thing. First we are going to find out the equation of Y1 of Z. And second we are going to find out the equation of Y2 of Z. So after getting the Y1 of Z and Y2 of Z, again we are going to draw. So this is the Y1 of Z direct form and this is the Y2 of Z direct form. After connecting these two things, we are going to get Y of Z, that is equal to Y1 of Z into Y2 of Z, which is in the form of cascade. So we have connected these two things. That's why it is converted into direct form to cascade form, that is Y1 of Z into Y2 of Z. So like this, we are going to draw the FIR filter, or we are going to design the FIR filter with the help of this direct form as well as the cascade form. So I think it is very clear how this realization is going to happen, how this FIR filter are going to realize with the help of two things, which is direct form one and cascade form. So in the next lecture, I'm going to discuss the another technique, how this FIR filter is going to design with the help of a Fourier series method. So thank you.